Okay. I'm just going to include the new engineered features into the features list. And then we're going to split into train and test. So we're going to create train real, which is going to be all of the data before day 8 and all the data after day 14. And then we're going to create the test set, which is between it's day 8 all the way up to day 14. Okay. Okay, so now we're going to make the negative samples. In variable features, this is the features that you're going to choose to change. Source user domain and destination user domain are actually very highly correlated, as are source computer and destination computer. So it's up to you. You can leave them in. But if you take them out, you actually might get slightly better results. I don't know. That's up for you to experiment with. Everything else seems to be fairly uncorrelated. Okay. Yep.
The way you split the train and test was based on days?
Yeah. So day 8 is when the red team campaign really starts to kick into a high gear. So it kind of looks like this, and then it goes up like this, and goes down slowly. So day 8 is when the red team event starts, and it kind of fizzles out around day 14, 15. So so I'm taking all of day 8 to all the way up to all of day 14, and that's my test set. And then everything else is my training set.
So you want to have the most concentration of those flagged events in the test set?
Sorry?
You want to have most of those anomaly cases in the test set?
Yeah.
And what's the purpose behind that?
I'll leave something to find. It's also that I don't want to overfit. Okay, so it's so that you actually have anomalous events to find. Otherwise, the options are limited. We could train on the entire data set and test on the entire data set, but I don't like doing that because you don't know who you overfit. You could train on the first n days up until day 8 and then test on that, but I don't like doing that because you don't build up enough of a profile of what's normal, right? So I figured this was the best of both worlds. I know it's a little weird taking your test data from the middle of the time series, but that's also one of the reasons why I dropped the seconds and tried to make it just independent of time in a way.
Right. So would this change the distribution between our train and test set?
There is a change in distribution, which is why your validation set is also going to be a last portion of the training set, so that you have a sense of you're trying to make sure that it's not overfitting just to this distribution, that it's able to generalize to other distributions.
Right. I mean, usually you want your validation set and the test set to come from the same distribution, even if they are different than the train. I mean, the train can come from a different distribution.
It's a time series problem. If something evolves over time, I would not have my validation set coming from the same exact same distribution as the training. I would have it come from a later point in the sequence of time, because that's what your test set's going to be. The validation there is to inform you that you're not overfitting to the train. If they're coming from exactly the same distribution, then you're going to have the loss values are going to be in lockstep all the way through.
Yeah, but the idea is, for example, in the validation set, now you're optimizing your model based on a specific distribution, and in your test, you're testing it in a different distribution. So you optimize on a distribution which is close to the train. Okay, not bad. But then when you want to test your model, you're actually testing it in a different distribution. So as if you're shooting, like you optimize somewhere.
But that's data science. Like you're always going to be testing on a new distribution. And that's why your validation there is to make sure you look at the loss function, and if the loss of the validation starts to go up, you know that you're overfitting to the train, and you know that it's not going to perform as well with the test. You don't know how good it's going to perform with the test set, but you know it's going to perform worse than it could have because it's now overfit to the train. So that, I would say that validation is more important to keep you disciplined. It's not there to make you, it's very easy to get comfortable with the validation set and think everything's rosy. But I think a validation set should be challenging to the model.
Right.
But I see your argument, and it's a fair point. It's just I take a more pessimistic view on model performance. So.
Right. Yeah, maybe we can have a discussion.
Yeah, sure. Okay. All right, so here we're going to calculate the distributions. Just getting the value count, so we'll go through each feature and get the value counts on that. Obviously, it's not normalized, but we'll normalize it later as we go through. I really should have actually normalized that outside of the for loop, but oh well, it's still pretty quick. This weird line of code, which I probably could have done cleaner, is just the ratio of negative samples to real samples. So it's the length of the, so I'm saying how many real samples are there? I'm going to create some real samples for every feature that I'm going to vary. So I divide into that, and then I multiply it by roughly the number that I want to create. Okay. So I'm going to create a data frame for each set of fake features. So there's going to be one data frame for the first feature, a data frame for the second feature, and so on and so on. And so I'm going to populate them into a list. It's better to populate them into a list and then concatenate them than to concatenate them in the for loop, because I think appending its complexity time is like linear, but if you do concat, it's quadratic, so you don't want to go there. Okay. So then I'm going to iterate through every feature and calculate the distribution. And then according to however I set my sampling, I'm saying most probable here. So, okay, I just say that the distribution is according to the distribution calculated. My values are going to be just a random choice from the distribution according to how many times it's going to make that random choice and according to the distribution values. So these are the possible choices it could make. This is the number of times it has to make that choice, and this is the distribution that it chooses it from. Okay. So then we will create our random sample. So I hope you guys are, if you're running through the code with me, I hope so. If not, it's not going to take too long to catch up. Okay, so, okay. And this is like, you can see that's pretty quick. Like, actually that was less than a second, so that's great. Yeah.
So you're sampling based on the probability distribution of the actual data?
Yes.
The random sample. So shouldn't it be like, don't you end up with the same data set that you started with if you don't do that?
You end up with a lot of collisions. So what I ended up doing, and maybe you're better off doing uniform.
Yeah.
What I end up doing is joining with the real data and trying to figure out, well, how many collisions do I have, and throwing out those.
Okay.
So
That makes sense.
the previous method I had was more careful about that, and it wouldn't create any collisions, but it would take hours. This took no time, so that was, yeah. I decided it's dirtier, but it's faster, yeah. So I didn't code in the least probable, but that wouldn't be a very difficult thing to code in as well. So, you know, just invert the distribution and normalize it again.
Yeah.
Okay. So this is where we get rid of any collisions. So already we just create a value that says already exists. We join it with the fake. I'm concatenating the list here to create the fake data, and then making some space, deleting that. But we're merging it here with the real data. And then anything where this value is null, you know that it didn't collide. So we're just going to select those values, right? That's just a nice and easy way to do it. Okay, then we create our labels. We concatenate it into our training set. We look at our distribution. So we have roughly 10%, a little bit more, is real. The rest is fake. So negative samples. So I'm going to sort them then by date. Okay, because now I want to make sure that my validation set is at the end of the sequence. That was a choice I made. You can play around with that here. You can see how it performs. Okay, thank you. Okay, so now we're actually getting down into training the model. So here you have the two choices of, do we split according to time,
or do we split according to randomness? So I found that splitting according to time gives me a more informative, more reliable validation set. Weirdly, I often get better performance when I split randomly in terms of the anomaly detection. But I wouldn't put too much weight on that metric because I don't want to bias my model selection too much based on the test data, right? But I still was able to match the highest performance from the random validation to the validation split in time. So I was still able to reach the same levels of performance. Just consistently, probably slightly better with the other one. Okay, so we're going to split the data here. So we now have our training and validation. This XGB.dmatrix function is really just to package up the NumPy values into something that the XGBoost algorithm can ingest. Okay? All right, so this part here is probably where you're going to be spending most of the tuning with the model. There's a lot of different options you can choose. I would recommend going to the XGBoost parameters page, which I think is here. So you can see all of these different parameters that you can put in. So you can choose what kind of algorithm you want to use. You can choose how much feedback you're getting from the model, threads, whatever. Then you can do your learning rate. You can do things that would allow for more complex models, things that allow for regularization. So let's have a look at a few of the things that I chose. Okay, there's a very high learning rate here. This is actually the highest value that you can have for the learning rate. Otherwise, it's just going to crawl along. For whatever reason, I had to boost it all the way up to the top. Not really sure why. Because I chose Booster Dart, that supports a kind of stochastic training. So it's similar to Dropout, which some of you might have heard, where you're dropping certain inputs into the model and making it less reliant on the combination of inputs. Max depth is really just how complex you want this model to be. So it's just like a tree. You know, if you add more depth, then it's going to be able to do more complex nonlinear things, but it's also more likely to overfit. So that's why I kept it at 3. If you go larger than this, it tends to overfit unless you get really, really heavy-handed with the regularization. Lambda is just L2 regularization, which hopefully you're all familiar with, but more or less what it is, it's a correction to the loss function that just punishes parameters from getting into certain values that cause your function to overfit to whatever value there is in the training data. It just smooths out that function a lot. Okay, objective, we're just using binary logistic. That's pretty simple. Our evaluation metric, that's just, so we're evaluating the loss function, just log loss, binary log loss. We're looking at the area under the precision recall curve, and we're looking at the map, which is the mean average precision, I think. It's not too informative, actually. You're probably just better off with just the area under the curve, but I'll leave it in there for anyway. Scale positive weight is class weighting. So we learned about this last week. Normally, the positive class is the smaller class. Here, it's actually the bigger class. So I'm giving a small value. Normally, this value should be an integer and going quite large, but because it's actually the 0 class, I'm just giving that small. I'm giving a very small value here. So this means that I'm making the loss for the fake data to be smaller than the loss for the real data. Okay. Tree method GPU hist is just kind of get it training on the GPU. I think it works a little bit faster here on this GPU. Not a whole lot, but it definitely speeds up training. Verbosity is just to say how chatty do you want your XGBoost to be. You can have it 0, so it doesn't say anything. 2, it gives you all the errors, and 1 is just about the right level. Unfortunately, I don't have a verbosity setting myself. Okay. And then what do you want to evaluate? You want to evaluate the validation data and also the training data. And then finally, the number of training iterations that you're going to run through. Okay. Right. Okay, so let's train it. Well, actually before, no, let's just train it. Yeesh. All right, I was looking at the wrong value. That's good. Okay, so our training loss is going down. It doesn't drop massively, which, yeah, it's not great. And maybe it's possible that we've picked fake samples that are too challenging. So this is really a question of striking the right balance. And our validation loss actually is blowing up today. Okay. Why is that? Sorry? Yeah, if I uncomment it, maybe. I found out it was very unstable before. Huh. Okay. So this is new. Normally, it doesn't actually continue to increase in value. So this is actually going to perform really badly. I'll just scroll down and show you the results before I get rid of them to show that it's true. I did actually get good values. Okay, so we can see how the model does with the validation set. So this is still using real data and fake data. So we can get a precision of 50%, recall of 50%, and accuracy of 86% in this case. So not amazing. But your distribution is more or less fitting the true distribution of the data. So you've got more fake data than you have real data. Now, let's use our test set. So we're going to change the label here. The label is going to be the value red. So we want to make sure that the label is actually, this was a red team event. And we're using on the test set, so that is that chunk of time in the middle of the sequence. And so we get a precision of 70%, recall of 75%, and an accuracy of 99%. What does that mean for an anomaly detector? Well, if we sort these values, so we go from highest to lowest, and we look at the top 100, we get 29 in the top 100 are anomalous events out of 40. So it can perform well. This is not going to perform well to date, this one.
I ran it, the validation loss is going down.
Okay.
Kind of got the same results for the training as the previous results.
Great.
Yeah, so maybe if you run it again, it will work.
Why did they do that? I'm just curious to see where this is going to go then, because it's going to probably give. Okay, you might catch a few. 10. Still caught 10, and that was like kind of terrible. And the distributions, okay, it would be better if the anomalous distribution was pushed more towards 1, but still the smallest value is 0.4 something, whereas the average here is around 0.4 something, right? So there is a distinction between the two distributions. Okay, so I'm going to take a little break here and quit melting your brain talking to you. I'm going to give you some time to play around with this. Feel free to choose whatever you want to do. You can change the fake data. As you see, it's pretty quick to generate that. Make sure that you're keeping track of your RAM. If you're generating new fake data, delete the old stuff if you're renaming things, because you don't want to blow up your RAM. Play around with the regularization, play around with the depth, the training rates, your classifier, whatever you wish. And if you have any questions, we will be here to help out. Yes?
I have a quick question.
Yep.
So for the XGBoost model, is it possible to set it so that the number of round is dependent on the performance of the validation?
Yes,
Okay.
it is. That early stopping is definitely an option you can
Oh,
set.
okay.
I haven't done it in a while, so I'm not. The code is not offhand. But if you look it up in the documentation, it's pretty simple
Sure.
to put it. Yeah. So now I'm doing it with the dropout, and yeah, it's behaving a bit better, slightly. Ish.
Yeah. Yeah. Cool. So that's. Oh, I just uncommented rate drop. Yeah. Sorry, I should just call it what it is. It's rate drop. It's not actually dropout. Okay. Let's see. So I swapped the labels. I just want to see how that performed. Similar-ish performance. Yeah. Now I'm getting 0. So it's definitely not. Okay, there's probably a bug there. So I need to go and check that out. So this is what happens. You shouldn't edit your code live. So I swapped the labels in a few places. I'm here. I'm going to swap it back because it just wasn't performing well. So the red team labels should match the training labels that you give to the classifier. So train real should be, I'm going to go back to it being 0, but not to 1. I'm just going to run everything again. Okay, so what's your name? Sorry. Yeah. Fatin. Okay, so Fatin noticed that typically, as you play around with the values, you seem to constantly get 8 out of 30. You always. Oh, sorry. That was sorry. I'm really sorry. I thought you were just chatting the whole time. Sorry. Okay. Sorry, and I'm really bad with names. Venom. Okay, Venom had noticed that you often get 8 out of 10 as like that's kind of the worst performing value, but you seem to consistently get this 8. It's my intuition that this would be typically the most noisy actions that the red team made, and that they were the most anomalous. So it's good to know that that you can at least grab some as you tune these values. And the thing then you can consider is that you could look at these events and use your human knowledge to say, okay, well, this event followed by this event and this event, maybe they're all bunched together, for example. And maybe you could say, well, what is the event that led up to this event? Like, did somebody have to log into this system to do this? Is there anything I can chain along? So grabbing consistently the same values is probably a good indication that you have something very, very strange there. You could maybe do an ensemble model, maybe if you wanted to see different thresholds and different parameters, do you consistently get the same results? And maybe then this is something that you might want to focus on slightly more. So we were using tabular data here, but you could format this whatever way you wanted. You could easily build a graph, for example. So we have computers, we have talking to each other, we have domains, whatever. Edges could be just the frequency of connections between these things over some period of time, so the graph could even be dynamic. And then you could create fake edges. So is this a real edge or not, for example, and then have a classifier deal with that. You could do sequence modeling. So you could use a neural network to perform this task, grab those embeddings, and then feed those sequences of embeddings into a classifier. Again, your negative class has to make sense. So the next step in that negative sample has to be consistent with the previous step. So I don't really know how you would generate that. That is a research project in itself, but that would be a really interesting thing that you could maybe do. So the point being that this is actually a very powerful data set that you can use a lot of different models for solving this problem with. Definitely a lot of different approaches you could take. I'm wondering if it would generalize well. I'm not sure how you could make this generalize in your own environment, other than what we were teaching last week, maybe. But that would, yeah, it's maybe actually that would work. Maybe you could combine these two things. Who knows? Okay, so I rerun that. Not great loss function. It's behaving really, really weirdly than before. But I'm still catching 10. So that's, yeah, that's not too bad. Oh, I think I know why. Yeah, I need to bring down this. I'm just going to kill the class weighting and just see how it performs again. So I encourage you guys, you know, if not today, over the week, play around with this, see what parameters actually work, see what distribution of of negative samples actually help, what kind of performance you get with uniform versus most probable. And yeah, I don't know, does anybody have any questions on the code or the theory? Do people feel this is a lot more accessible than last week's?
One thing I can do, I get this data. I wanted to work on another data set, but I can get this data and see if I can detect any red team activity through graph. That would be really great.
Okay, I'll share with you my my sampling code.
Yeah,
and then
yeah, exactly. Like do the same sampling, but I detect to see which one is better. Or
yeah.
also different.
Oh, cool.
I do my
It's
best.
going to be a competition.
Yeah, I know, right?
Damn.
I thought it always is.
All right, so here we have 8 again. Yep. So consistently 8 values. You can see if you don't do the class weighting, you still get a very that one. Yeah, if you don't do the class weighting, you still get a very high value for
The normal data. So that's a problem. So that's also why the class weighting is kind of important here. Okay.
I have a question. I don't know the answer, like maybe so many of you use it, or maybe it could be answered from the MLOps workshop. If some like data changes, right? How in the production environment, how do you address something like that for people who work data science model in production mostly?
Like what
Issues like that, right? So if the data change, sampling and everything have to be changed, right?
Depends where it's changed.
Like it changes.
Do you mean like if you get domain drift, or if a decision is being made to like
There's a new value.
New values, right?
new parameters? Yeah.
How often should we update? The MLOps team should tell us that question, like answer that question.
Should they be agile?
But you cannot be agile in production.
No, I know. Yeah.
Why not?
It's like when you put something in production, it's really hard. Like you have to keep testing, integration tests and everything, right? You don't want every 2 weeks spend lots of time on that. Imagine you have 30 AI models, right? You cannot manually investigate all the models all the time.
Yeah, but I'm sorry, like you mean agility just means like just getting rapid feedback, right? And rapidly.
Yeah, but it's all like move fast and
Somebody have to look at it all the time, right?
move fast and break things, people say, but you're really going to break things if you're getting agile with a production environment. Like you will break things a lot.
Yeah.
So it probably is.
I think it depends on the kind of model you're using.
Yeah, like I was like, this happens, right? One of us run exactly same code and the result was different, right? We couldn't find an answer why it was different. It was different. Especially the ones like have like random, like they initiate some random weights. So each time you run, there's a chance that it will be different.
Well, yeah, and That's actually true. That's a real problem. Like seeding can help, but things like if you're doing deep learning and you're using Atom, we actually literally had to repeat experiments again and again and again because there's perturbations that are brought in from the Atom optimizer. So like seeding random numbers sure can help, but it can only take you so far for certain algorithms. I just wanted to say that, so I changed the class weighting again to just, again, back to this low value of 0.1. As you might have seen before, the average was around 0.8 here, and now the average is around 0.35. So class weighting can really help push things to whatever way you want. If you have an appetite for false positives or false negatives, it depends on what you're willing to take. Here, you really don't want to have an appetite for false positives. Otherwise, you're just going to get just a deluge of info, and you're not going to actually know which of these is a threat.
This is a class weight like 0.1?
Yeah, 0.1. Still catching those tricky 8 that are constantly just hanging out over here.
Oh, you switched the labels as well.
Yeah, I went back to the regular labels, so the ones that I had been using before. I found that wasn't working. I might play with that at home at some point. Okay.
At long weekend. Cold.
Oh, like next week. I'm sleeping all weekend. I haven't slept in 6 weeks.
Okay.
Okay.
So the class weight is 0.1, which is the original ratio.
Yeah.
Yeah. Okay.
I mean, I think I would treat it more as a hyperparameter. Sorry, where was it? I would treat it more as a hyperparameter than less. This is not as important as, say, doing regular supervised learning, where you should probably keep it close enough to the ratio. But it's more, I use it as a hyperparameter to say, like, okay, well, what's my appetite for false positives? So if I can skew it more that way or this way. Yeah. So if I was changing things here, you can increase the depth because it's quite a conservative depth, but you will probably find the validation loss exploding. So if you increase the depth, then also consider increasing your regularization, your lambda value, or your rate drop. You cannot, unfortunately, increase the learning rate. It's already maxed out. So that's somewhat of a problem. I don't know. I don't think there's much more to cover. This is kind of like overshooting, undershooting, isn't it, in terms of complexity? This means Saharis is going to nail it in terms of complexity.
Alright. I like this the way it's formatted.
Okay, could you guys do the survey? Not speaking of that.
Oh yeah, survey.
Yes, please take the survey. It will really help us.
Oh.
It takes like 1 minute. Thank you.
Yeah, and for those online, please take a survey. Yes. Yeah.
So you prefer this one over last week's activity?
Well,
The way.
yeah, because like everything is kind of laid down already, and now you can just experiment, right? Like it's getting to the point of like doing, working on the concept
Rather than the code.
rather than the code.
Yeah.
Because like, what's
Okay.
the point of like writing pandas data frame of like filtering things and things like that?
Yeah, no. I poorly chose how to delete some of the, or fill in the blanks.
So everybody is agree with that, so you just want to know. So I just want to see like next week
What to
which
do?
one you prefer.
I would avoid fill in the blanks for everyone's sanity.
Okay, already agree.
Yeah. You had a question.
Yeah, I'm just wondering, have you also looked at other advanced like gradient boosting algorithm like GBM?
Yeah, I mean they're all pretty much the same gradient boosting model, right?
I think similar, but yeah, I think they're close. Yeah.
Yeah. So I might have used like GBM before.
I think I use it personally. It seems to be faster than XGBoost. Seems to be.
Now there is 2 ways you can ingest XGBoost. There's a regular XGBoost, and then there's a crappy scikit-learn wrapper.
Okay.
If you're using the crappy scikit-learn wrapper, it's going to perform a lot worse.
Okay.
So generally, I would recommend everybody avoid scikit-learn as much as possible as a data scientist. It's just so badly coded. It's great because it's a great resource, but there's better stuff out there. Once you get to know what you're using with scikit-learn, you'll get tired of scikit-learn. You'll be like, I want something better than this. A perfect example is like precision recall curve. pick like 3 random thresholds and that's it. It's garbage looking compared to the precision recall curve. Anyway, sorry, I'm on a rant. But their XGBoost version isn't very good.
Sure. Thanks.
Okay, so I'm going to stop sharing my screen. If that's all right.
So we're done.
More or less. 10 minutes
Okay.
ago. You're free to go.
All
But
right.
don't forget to fill out the survey,
This
please.
is your last lecture. Let's give a call.
Yep, exactly.
Thank you.
Thank you very much. Thank you for agreeing to give 2 courses rather than 1.